Well, welcome everybody. Here we are on a snowy day, and so I'm going to give you a lecture for today, which is January 29th, 2019. Before I do, I just wanted to go through what we have done last week and then continue on with a lecture about slope distance, and horizontal distance. Uh, so basically, last week I had you look at this alternate assignment, the video on drafting field notes. We're going to get back to that in a little bit when we start looking at area calculations and those sorts of things. But again, you really need to go ahead and take a look at that and make sure that you feel comfortable with that material. I know we're still waiting to get the drafting kits, and as soon as they come in, you'll be able to handle this. Um, and there's some field notes that are going to be used for that drafting exercise. When you're complete with that, then you're going to do another drafting exercise with the data that you collected 2 weeks ago. And when you're finished with that, you're going to do a third drafting exercise where you're going to take the data that you collect starting this week. So those folks in the Tuesday lab today, don't sweat. We'll get out next week and we'll start collecting some of that data. Okay, should only take about one lab period to go out and collect the data, and then another lab period to work the data up. So we'll get all caught up. We'll be just fine before you know it. I did want to introduce you, and I will do this in lecture on Thursday this week on the free land surveying tool. You can get online and check it out if you want, but I'll go ahead and demo that with some field note data. Okay, and so this week, what we have is for the alternate assignment, and it'll actually say horizontal. It'll actually be you'll see this video here, so you obviously you'll go ahead and play the video, but the actual lecture notes are on this Word document called slope distance and horizontal distance. Okay, so I've got that opened up already. Let me see if I can pull that open. All right. And this is what it looks like. So basically, we're going to be looking at this concept of slope, all right, and different units by which we measure slope, and what slope distance is, why it's important, and how we convert that, and why we need to convert it to horizontal distance and for the purposes of mapping. Okay, so the whole idea, and we realize that there's lots of different shapes and sizes of triangles that are out there. What we concentrate on is this thing called the right triangle. Okay, so the right triangle, a good place to learn about the right triangle is at this website. Math is fun. All right, so I've got that website open. I'm going to bounce to it here. And this is basically, it's kind of an introduction to trigonometry. So it's trigonometry is all about triangles, but the one that is important that we're going to be looking at is this thing called the right triangle. And the right triangle is actually very unique in that one of the corners is 90 degrees. Okay, then the other two could be combinations of two other things that add up to 90. This could be 60, that could be 30, and that's 90. So inside the triangle, if you add up all the angles inside, it equals 180 degrees. But in the right triangle, one of those corners is always 90. Okay? So a symbol that we use to measure the angle inside that is often used as we describe as theta. Okay, so theta is that funny little circle with a line going through it. Now, when we're talking about the right triangles, we can actually use theta can actually be used to describe the ratios of the various lengths of the sides compared to one another. Okay, we'll take a look at that in just a minute. But before we do that, theta is usually measured at the angle on the bottom that's connected to the 90-degree angle. All right. So that's usually what we consider to be theta. And so if we're measuring slope, this would be the horizontal distance, this would be the slope distance, and this would be the vertical distance. Okay, and but we call it in the right triangle. You may recall from math, we call the long sloping side, the longest side of a right triangle, is called the hypotenuse. Uh, the one that is next to that, the one that's adjacent to the hypotenuse, or the one that's adjacent, sorry, to theta, is this one on the bottom, or what we call horizontal distance, and the side that's opposite of theta is this vertical distance. So we call it in trigonometric terms, they call it opposite, adjacent, and hypotenuse. Okay, so that's how they're described here. So the longest side is the hypotenuse, opposite is the opposite of the angle theta, and adjacent is adjacent to the angle theta. All right. So why is this knowing this theta important? They give you a couple of examples. You could read through it on your own. But one that they show here at the bottom is, let's say you have a distance that you've measured, okay? And in this case, they're asking you want to know what that height is. You couldn't directly measure that, but you could directly measure the angle theta, all right? So these two pieces of information are enough to calculate this, because it's a right triangle, okay? Conversely, what we're doing is we a lot of times are measuring up a slope, and we want to know what the horizontal distance is. So in that case, we actually can use this value of theta and that slope distance to calculate this what they call the adjacent side of the triangle. Okay, so how is that done? Well, so moving on down, this introduces the concept that's used for particularly for right triangles, this idea of sine, cosine, and tangent. And they look fancy and all that thing, but really what it says is the sine function of theta is just simply the ratio of the length of the opposite side to the length of the hypotenuse. So if I know this distance and I know that distance and I divide this by that, it gives me a decimal number, which is essentially the sine of theta. So whatever this angle is, if I hit the sine button, it gives me the relationship between this side and that side. Pretty cool, huh? We don't use sine so much in our work with forestry and measurements of slopes. What we primarily work with is cosine function, and you'll see a little bit later the tangent function. Okay, but the cosine function is if you are measuring a degree, excuse me, you're measuring an angle in degree slope, then you can go ahead and use the cosine function. Because if you think about it, the hypotenuse, this right here, that's the slope distance, and the adjacent is the horizontal distance. All right. So like I said, if we're able to measure this slope in degrees, and if we measured the slope distance through this cosine function, we're able to calculate what the horizontal distance is. Okay, so they give you a little example here. What is the sine of 35 degrees? So that's the angle. Okay, and they go ahead and they basically sine of 35 degrees is 2.8, because this function is basically looking at the relationship between the opposite and the hypotenuse. So the opposite is 2.8 units divided by 4.9 units, and the answer is 0.57. So essentially, if you typed in on the calculator 35 and then hit the sine function, that's the number that would pop up. Okay, it's pretty simple. I'll give an example. So every calculator has got or every computer has got a calculator on it. And when you open up your calculator, it might look like this, all right? But you have and it might say standard, but you can actually convert that to a scientific, and then you have your sine, your cosine, and your tangent function. So here is that 35, and I just hit the sine, and voila, there's the 0.57, okay? So that's all it's doing. It's just, this number is just saying, regardless of what the actual distances are, this side is 57% of that side, and that's what that angle is measuring, okay? So let's take a look at the cosine function. So we'll go we'll go, let me clear that. We'll go 35 degrees, hit the cosine function. That says 82, okay, basically 0.82. What it's saying is basically this side, the length of that side is essentially 82% of the length of that side. All right, let's give her a try and see if it's right. 4 divided by 4.9 equals, well, what do you know? 82%. So 4 is 82% of 4.9. Okay, so you see that relationship, and it's really cool. You could use that, you know, all over the place for a lot of different things when you're dealing with right triangles. So, you know, they show some examples that if you have, if you happen to know the slope distance, I don't know how you get that, to the top of a tree, and you knew the angle in degrees, you can calculate what the height of that tree is, okay? So that's some of the things that they're kind of showing you in here, and you can kind of play around with that a little bit. But the thing I wanted to point out is this, just this little circle that they have here, and I'm going to go ahead and turn the angles on so that you can kind of see. What's interesting is if you take note of these numbers up here, I'm going to move this cursor down here, and notice that it's set at 360 degrees, okay? So on this, a lot of times when you're measuring angles in math, they start from this line here. That's the 0 line. And then you notice that the degrees, if you look at the top, you'll see it's getting larger and larger and larger until 90 degrees is vertical, okay? That's kind of how we actually do it when we're measuring slope too, out in the field, okay? Horizontal is 0, and then we measure either the slope above it or the slope below horizontal. So that's kind of an important thing. It's different than looking at north on the compass. All right, so the thing that this points out in a very cool way is if I move this cursor up to, let's say, 30 degrees, it gives me the relationships of all three of those sides, okay? In the cosine, the sine, and this tangent function, okay? So let me go back and redefine what some of these terms are. The cosine function is looking at the relationship between the adjacent and the hypotenuse, okay? So at 30 degrees, the adjacent side is 87% of the hypotenuse, okay? The sine function is looking at the relationship between the opposite side, or that 0.5, and the hypotenuse, which is the sloping line, okay? So basically, at 30 degrees, the height, or the side of the opposite side, is 50% of the length of the hypotenuse, okay? And then the tangent function is not looking at the hypotenuse at all. It's comparing the opposite and the adjacent side, okay? So notice that you have you have the opposite side over here and the adjacent side down there. And what it's saying is that the opposite side is basically about 58% of the adjacent side, okay? So it's not looking at the hypotenuse at all. It's looking at the other two sides, okay, comparing them. And that's important when we're actually dealing with percent slope. And we'll get to that in just a little bit, okay? But this is kind of a fun thing to take a look at. Check this out. If I get to a 45-degree angle, notice that the tangent function is 1. In other words, the opposite and the adjacent side are equal, all right? And that's kind of an important thing to remember. That is basically 100% slope. A 45-degree angle is essentially a 100-degree slope because the opposite and the adjacent are exactly the same length. All right, so again, that's kind of fun to play around with. If you want to get out there, I've given you the website. So resuming back to our handout here, I want to highlight a couple of things for you. We concentrate on degree. When we're measuring in degree slope, if the clinometer or the unit that we're measuring in is in degrees, and there are a lot of them out there, theodolites, surveying equipment always measures in degrees, then the angle that you're looking at, this theta angle, is always comparing the hypotenuse, or what you're always using is the cosine function. You're always comparing the adjacent to the hypotenuse, okay? We tend not to use this so much when we're doing degree slope. When we do percent slope, we start comparing the opposite and the adjacent, okay? So let's get there. Let's take this slowly. Notice that we are using the cosine function for this. So degree slope is basically when the slope is measured in degree units. Same units that we use in the hand compasses, okay? Only, again, 0 degrees is looking along the horizontal, and then we measure degrees above it or degrees below it. So in this case, we're looking at the horizontal, this is the horizon, or 0 degrees theta, and we're measuring up a slope, okay, of 500 feet. So somebody pulled the tape out, and you're measuring 500 feet here, and now you've got this. You pull out a angle measuring device, and it measures that from the horizon up to the top of that slope. It's 22 degrees. Okay, so if the slope is measured in degrees, then to convert slope distance to horizontal distance, you do it with the cosine function. And it's really simple. So the slope distance is 500 degrees, theta is 22 degrees, and it's just this formula right here. Cosine of the degree slope times the slope distance. Okay, let me whip out the calculator and let's take a look at it. So essentially, I've got 22 degrees. I plug in 22, I hit the cosine function. It says that basically at 22 degrees, the horizontal distance is roughly 93% of the slope distance. So you would expect this to be pretty close to 500 feet. Okay, it's about 93% of it. So essentially, again, let me clear everything so you can see I'm not doing anything magic here. Okay, so 22 degrees, hit the cosine, and then I multiply that by the horizontal, by the slope distance. Okay, boom. Okay, 463.6 feet. Okay, so that's the answer there. So that's kind of cool. So what happens if I'm measuring downhill? All right. Uh-oh, now I've got a negative 22% slope, because remember, this is 0, and I'd be measuring down slope from it. All right. So let's try it. 22, I'm going to make it a negative 22. Okay. Hit the cosine button, and oh, look at that. It made it positive. It doesn't care, right? It just says, oh, that relationship is the horizontal distance is 93% of the slope distance. That's all it's saying. And so now I multiply that by my slope distance, 93% of 500, is 463.6 feet. Again, so it's the same horizontal distance, all right? Kind of cool to think about. So the thing is, we don't really do it. It's important to know this because I'm going to show you kind of a way that ultimately you'll be using this calculation. But the problem is that the tool we like to measure in, because what foresters and engineers and other folks like to use is this idea of percent slope. All right. And percent slope, another word for it that you might hear is called grade. You're ever driving down the highway and you see 6% grade? Okay, it's exactly the same thing as percent slope, right? So I'm still using that term theta to describe that angle in there, okay? Only the theta, the units are going to be in percent units rather than degree units, okay? So when we're dealing with percent grade, you're dealing with this unit that we call percent. Okay, and all percent really is the relationship of rise over run. You may have heard those terms in the past. All right, what does that mean? Well, it just simply means opposite over adjacent. Okay, so there's the triangle we were looking at before, and basically opposite in engineering terms is often called rise. It's just the difference in elevation between your horizontal line and the top of your slope, okay? And run is just your horizontal distance. So what you'll hear engineers talk about, you know, rise over run in percent slope. And so all it is, it's this number, this length, divided by that length, okay? So if you could see right here, let's see, I have you calculate percent slope by taking rise over run, and that gives you a decimal, right? And so to convert it into an actual percent, you just multiply it by 100. Okay, so let's give this a run here. I mean a rise. I mean, let's just give it let's whip through this thing here, okay? So here I've gone up this slope here, okay? And, or I'm shooting an angle with a percent slope tool, okay? And so I take it back. I'm not measuring the slope. I measured a horizontal distance of 100 feet on my run, and I've noted somehow I was able to measure that vertical distance, and that was 25 feet. All right, so there's my rise, and that's my run. I'm trying to calculate what this percent slope is. Okay, so I don't know what the percent slope is, but I do know what my rise and my run is. So I plug it into that formula. Okay, rise over run times 100, rise over run times 100. So 25 divided by 100 is 0.25, and then I multiply that by 100, and it turns it into 25%. Pretty simple, right? So no sine, no cosine, no nothing on it, right? We will be using the tangent function in just a minute, but I'll be talking about that in a little bit. Okay, so let's say it's going, so that's, you know, that basically it's a positive number because that's a positive 25 feet. That says that it's a slope 25% going uphill. Well, what if that slope is actually going downhill? Well, I know, you know, if this is, you know, the horizon here, that's 100 feet of run, and I've dropped 25 feet from where I was, so that's a negative 25 feet. So in this case, I'm trying to calculate the slope. The run is 100 feet. The rise, or anti-rise maybe, you want to call it that, is negative 25 feet. So, oops, I should have a 25 in here. Sorry, let me a minus in there. And so let me plug that in. I go 25, make it a minus, divide that by 100 times 100, and it's minus 25% slope. Okay, so all that minus sign is saying is that you're going downhill. Okay, all it's doing is it's letting you know that you're going uphill or downhill, and it doesn't change the number one whit. All right, so that's kind of important to note. All right, let's try another example here. So if I've gone up 25 feet for every 100 feet I've gone out, gives me a percent slope of 25. What if I've gone out 150 feet and still only went up 25% slope, or 25 feet? Is this going to be a steeper slope or a less steep slope than this? Well, let's find out. This turned out to be 25%. Okay, so here, in this case, my run is 150 feet rather than 100 feet, and my rise is 25 feet. So 25 divided by 150 times 100 is incorrect. 25 divided by 150 times 100. There we go. Now it's going to work. I must have multiplied it by 1,000. About 17%. So it's not as steep, right? In other words, when I got out to 100 feet, which would be right about here, I've only gone up 17 feet. Okay, so it's not as steep. All right, so the lower the number, the less steep it is. Same case if I'm going downhill. All right, so again, this would be, and I've got a typo in there. I got to fix that. Okay, that would be a minus 17% slope going downhill. All right, so let's give these a try here on a couple of examples here. Okay, so I've got a rise of 29 feet and a run of 35 feet. It's going to be pretty steep because my rise is almost exactly the same as the run. Okay, so 25 divided by 35 times 100. And that gives me about a 71% slope. Okay. Let's try the next one. I've gone 150 feet out in 1 mile. I've gone 150 feet of rise in 1 mile. So 150 divided by 2580 times 100. And that's about a 6% slope. I'm just going to go to the nearest. Okay. Get the idea? 3 feet divided by 25 feet, rise over run, times 100 equals, that's a 12% slope. Okay. And let's do another one. We got, let's see, 11 divided by 250 times 100. That's, let's just say 4%. And then the last one, I think you can figure out on your own, is going to be 6%. So take a look at that. 150 feet in 1 mile is the same slope as 6 feet in 100 feet. Basically, it's exactly the same slope. For every 100 feet of run, I've got 6 feet of rise. Okay, if I just multiplied that, 52 times, I would end up with 150 feet of elevation. A 6% slope, if you ever notice that, when you're heading down from Asheville to Old Fort, and you start going down that really, really, really steep slope there, you are going down about a 6% grade. Okay, it may not sound like it's very steep, but if you're in a truck full of heavily loaded truck and your air brakes are not working, you got problems. All right, so that's an important thing. So some of the steepest roads we have around here that are like highways, I think Soco Gap down into Cherokee, I think you might see 9% slope. That's just as steep as can be. It's but those are the kinds of grades that we're dealing with on highways. Really the steepest slopes that you ever really want to see on a road, in even a private road, might be around 20%. And that's huge. Okay, over at the Beatty property, if you've been over there, that really, 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 really steep road that make people walk up, that's about 23% slope. Just to give you an idea. So you ask me, what does this have to do with what we're doing in class here? Okay, well, I'm glad you asked. Remember what we talked about, that that when we're mapping, we always, 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 always draw our maps in horizontal distance. We never, ever use slope distances. However, when we're in the field, that's the only thing we can measure is slope distance sometimes. All right, so we're going to get to that. How do we convert slope distance to horizontal distance? All right, the tool that we tend to use is not a degree slope tool. It's a tool that the clinometer, when you get it, you're going to see that it is in percent slope. And it also uses this other weird slope called the topographic slope. We'll talk about that later. But you will have a percent slope on your clinometer, and hopefully you've all by now have read your clinometer instructions and how you use it. And essentially you use it very similar to what that person is. I tend not to put it on my left eye though. It's kind of, that's, to me, that's weird what's going on in that picture. But usually you'll hold it by the little the brass ring down at the bottom. I usually hold it with my right hand and hold it up to my right eye. Okay, and how you're actually using this tool is you're just reading the gauge on it as you tip your head back or up or down. So here's Tom right here, and I know this is kind of a funky line. I have no idea why Tom's dressed like a ghost. It doesn't really matter, but basically, when they're holding the clinometer at 0, basically the clinometer is looking at what's Tom's horizon, okay? What's level with his eye, all right? So now Tom's shooting up at his pal up over here, and so the angle that it's reading from Tom's eye to, and typically what you're going to do is shoot at your buddy's eye, or somewhere on your buddy that's the same height as your eye, okay? In other words, I wouldn't shoot from here to there, because that's not the slope I'm trying to read. I'm trying to read the slope, the actual slope on the ground, that basically is this line right here, which, surprise, surprise, is exactly the same slope as from my eye to my buddy's eye, because, or where my eye is on my buddy, okay? So that's the slope I'm actually measuring, and we'll get some practice doing that in class, obviously. But it turns out that the angle above the horizon is 20%. Okay, so that's a 20% slope. So if I was to think about this in terms of 100-foot segments, if this is 100 feet, this would have gone up 20 feet. Okay, let's say that's 100 feet, gone up 20. If you've gone out 200 feet, then it would have gone up 40 feet. Okay, so for every 100 feet, it rises another 20 feet. That's what that percent slope is telling us. Okay, so we do have to measure on slopes. Okay, and again, like I said, you always draw your maps using the horizontal distance, never the slope distance. Therefore, if you are on a slopy ground, then you got to measure, you got to figure out what the horizontal distance is somehow. Okay, and there's two ways. One is, hey, I don't let the slope bother me. I just hold that tape as horizontal as possible. That's what we did on the last exercise. Okay, that's why I had you holding the tape up in the air and looking down to kind of try to make sure you were lined up with your mark. So you were just trying to account for this. You were just kind of taking the slope out of the whole picture, really. You could do that on mild slopes. When it starts getting really steep, then you have to start doing things like breaking chain. So here's the instance that might look like what we did. Okay, you just held the tape out and then measured the horizontal distance as best possible. Or you may have to break chain on a really steep slope. It's just so steep that you can't hold that thing horizontal. When you're, in this case, you're going from A to A prime, they're showing down there. And to get there, they had to do all these little short shots. Okay, and each time move down with the tape, hold the zero end up in the air, read the distance, and then go back, then have the rear chainman go to that point, have the head chainman go forward until they get the next horizontal distance. You add all those up, and that's the total horizontal distance between those two stations. Okay, so that's kind of a pain in the neck to do that. I didn't write this thing, so I'm not sure why they're calling it slopping ground, but it could be. Maybe after a while you start slopping around out there. Okay. Anyway, so moving on, that's one way of doing it. Okay, and we actually practiced that last week or 2 weeks ago. The other is it's so steep that you just say, forget it. I'm just going to actually measure the slope and the slope distance, and then I'm going to mathematically convert it to horizontal distance. Okay, so basically what you're doing is you're measuring slope distance and theta. Okay, that angle between the horizontal distance and the slope. Okay, so and it's really easy to do this if you're measuring it in degree slope. But again, remember, we're actually using a percent slope tool. So if we were using a degree slope, all we would do is run it through this calculation like we did above. You get theta, you hit the cosine button, multiply that by your slope distance, and it gives you the horizontal distance. The problem is what our percent slope is actually measuring is not the relationship between the adjacent and the hypotenuse. It's measuring the relationship between the opposite and the adjacent. So the number it's giving us is telling us this relationship, rise over run. So what we have to do is convert that to degree slope, and then we can use the cosine function. Okay, so how do we convert rise over run, expressed as a fraction, to a degree slope? Well, turns out that rise over run is the tangent function on a right triangle. So in order to take that relationship and turn it back into a degree slope, you have to use the inverse tangent function. The other method that you could use is like I was saying, if you're stuck on a big long slope and you wanted to go ahead and measure the angle in percent slope and then the slope distance, you can convert it to horizontal distance by following this handy dandy little formula right here. So in this case, we're pretending that the slope distance measured was 250 feet, okay, and that the theta, or the percent slope, was measured as 10%, okay? So basically what it's saying is for every 100 feet of run, there's 10 feet of rise, okay? That's what that 10% is saying. So what you want to do is, the first thing is you need to convert that percent slope to its decimal form. You got to get it out of a percentage and back to the original 10.1, because 10 feet of rise over every 100 feet of run is that decimal right there. Okay, so let me pull up the calculator. If I still got it. Okay, so 10 divided by 100 equals, okay, I think I did that wrong. Let's try that again. 10 divided by 100 equals, there we go. And but now I have to do the inverse of the tangent of that. Okay, in order to do that on my calculator, and you'll see on a lot of them have a tangent with a -1 sign over it. In order to get that on my Microsoft calculator, I have to hit the up arrow, and then I see that's the inverse tangent. Okay, so basically, when I did that, I took that 0.1 and I did the inverse tangent of it. what it gives me is the degree slope. Okay, so that's the slope in degrees. All right, then it's just a matter of doing that cosine function. So I have to go back to my cosine function. So cosine of 5.7 degrees is 0.99. So in other words, this distance is about 99% of that distance. Okay, so I take that and multiply it by my slope distance. Okay, there's the 0.995. I take that 0.995, which is just simply this, multiply it by my slope distance, 250 feet, times 250 equals 248.8 feet. So it's 99.5% of the slope distance. All right. So let's play this game a little bit. We'll give it a try. All right. So I may have to move this over just. Come on. Come on. Let's go. There we go. Get this. There we go, Mike. All right, so I've got a 12% slope. I convert that to a decimal, so that's pretty easy. All I have to do is put, I'm basically dividing each of these by 100. 0.20, 0.30, 0.40, 0.02, and 0.01. So now I have to convert each one of these now to degree slope by using that inverse tangent. So I'm just going to go 0.12, get the inverse tangent of that. That's about 6.8. I'm not going to get crazy with this. I just want to 0.07 inverse tangent is about 4.0. Okay, you get the idea. I'm going to let you do the rest on your own, but I'll just go through these two. And I'll do the one at the bottom too, because that's 0.01. Inverse tangent of that is 0.57. Okay, so that's the percent slope. I'm sorry, these are the degree slopes, okay, of these equivalent percent slopes. So then the next thing I do is I convert these to that cosine function right here so that I can multiply it by my slope distance. So 6.8. I'm going to go back to my cosine function. I hit that and it's 0.99. All right, let's go clear. We'll go 4. And we'll hit the cosine. Oh, look at that. 0.98. Not much difference, huh? And then let's go to that 1% slope, or that 0.5 degree slope, 0.6 degree slope. So we go 0.57, cosine that bad boy. No, look at that. It's 0.9999. It's essentially no difference. Okay, so on really not steep slopes, the horizontal distance and the slope distance are almost exactly the same. All right, for all practical purposes. I might have made a mistake on this other one. Let me go 6. Oops, clear that. 6.8 cosine. That was 992. So this is 992. What was the 4? Oh yeah, okay, so 0.4 cosine 0.998, 992, 9. We'll just see 998. Okay, so now all I have to do is I'll make this 0.999 just for laughs. Okay, so in order to get these answers now, I just simply multiply my slope distance by that relationship between slope distance and horizontal distance, and it gives me the horizontal distance of 0.992 times 179.5. So 178 point, we'll say 1. Okay? Did I need to do that? Absolutely. Absolutely. Okay? There's about a 1.5 foot difference between the two. So even though it's 99% of it, you still need to get that horizontal distance. All right? 220 feet times 0.998 is 219. So it's a half a foot difference. 18.6. And then let's see what the difference is between these two. I got 199.2 times 0.999 equals essentially the same thing. 199, 2/10 of a foot difference. Okay. So do you do those corrections? Yes, every single time. Okay. You've got the tools to do it. You just make sure that you get them done. So another way of doing it, though, and I've tried to simplify this for those of you who are not comfortable with doing the inverse tangent and the tangent functions and all that stuff, I basically have given you the cosine theta for any given, well, for every other slope. You'll see 1% slope to essentially 7% slope or 9% slope is essentially the same. Okay, so it doesn't change a whole lot. And once you start getting into steeper slopes, it does change. All right. And so basically, for any given percent slope, I look up the equivalent cosine theta and then just multiply that number. So let's say for 21% slope, or let's say a 20% slope, it's between these two, it's still 0.98, right? So this is 0.98 times my slope distance, okay? So it makes things a lot simpler, all right? Let's give that a try on this. So I've got, this is what your field notes would look like when you're actually doing this this week and next week when we're actually measuring our distances. So you got going from station A to B, you got a foresight and a backside, okay? I measure a slope distance, and then I measure the actual slope between those 2 points, and it turns out to be 5%, right? So how do I convert that? Well, I'll find 5% on here. Oh, it's 1. So it's essentially 157.2. That's the converted, okay? So here I'm going from station B to C. I've got a bearing of south 78 degrees west. Oh, I got, okay, 1 degree agreement. That's good. The slope distance is 223 feet, and the percent slope is 14. So I look up 14 on here. It's going to be 0.99. It's between these two. So I essentially take 223.1 times 0.99, and it gets me to 220.9 feet. Okay, so you can see it does make a difference. All right, let me make sure I did that right. 223.1 times 0.99. Just double checking. Yeah. Okay. So I mean, it trimmed off over 2 feet, close to 3 feet off of it. Okay. So actually over 3 feet, 3.1 feet, 3.2 feet. So that's important, right? When I'm plotting this stuff, I want to be really accurate with my horizontal distances. So you do those. Okay. Make sure that you do those. And so this chart is kind of handy for that. And I'll fix it so that it's more readable when you get it. So that's essentially what's going on with this. I'm going to be giving you a quick quiz on this stuff and how to do some of these conversions. Some of them are going to require that you actually get onto and open up the scientific calculator, because I'm going to make you tell me what the inverse tangent is. And then others, I'm just, all you really need to do is to look it up and make the calculations. Okay, so sounds good. We're up to 50 minutes, perfect lecture time, and I will see you on Thursday. You all take care now and have a fun day.